Hello and welcome to ElectroTuts. This is the part 2 of the series on timing analysis. In this video, we will look at timing analysis of synchronous sequential circuits. We will look at aperture time, clock to output contamination delay and propagation delay, setup time and hold time constraints, example, and clock skew. If you haven't watched the part 1 of this series yet, then do watch it before continuing because some concepts from part 1 will be directly used here. The link to part 1 of this series is given in the description below. Let's start with this tutorial. Consider a D flip-flop which is positive edge triggered. The flip-flop samples its input only at rising edges of clock and outputs the same value until the next edge arrives. Let's have a look at its timing diagram. Clock are usually square or rectangular pulses of a particular frequency. In this video, we will also see how to decide the clock frequency of a particular digital circuit. Let D input change randomly, but in a flip-flop, D is sampled only at rising edges of clock. This is how an ideal flip-flop would perform. But as we saw in part 1, practical circuits have delays. They need time to react. Similarly, we see that the input of a flip-flop must be stable for some time around the clock edge, or else the output may go unpredictable. This phenomena can be better understood with an analogy to camera. When taking a picture using camera, the object must be stable for at least aperture time. Similarly, the input must be stable for at least aperture time when the flip-flop samples the input, that is, around the rising edge of the clock. This time around the clock edge for which the input must be stable is called aperture time. Aperture time is divided into two parts: the time before the clock edge, setup time, and the time after the clock edge, hold time. We impose a condition on digital circuits that input must be stable at least setup time before the clock edge and until after hold time has passed. By imposing this condition on our sequential synchronous circuits, we guarantee that the flip-flops sample input when they are not changing. This was condition on input of flip-flops. Now let's look at the output of flip-flop. As we saw in part 1, the output of combinational circuit changes after contamination delay and settles to a stable value after propagation delay. In a similar manner, the output of flip-flop starts to change after some time and gets stable after some more time. In combinational circuits, these delays were measured from the point input changes. But in synchronous sequential circuits, such as flip-flops or FSM, the delays are measured with respect to clock. So, the contamination delay of a flip-flop is called clock to output contamination delay, TCCQ. Q is usually the output node of flip-flops. It is clock to Q contamination delay. Similarly, TPD is called as clock to Q propagation delay, which is TPCQ. Now we understand the basic terms. So let's see how we decide the clock frequency of a digital circuit. Flip-flop samples its input only at edges of clock. So if we increase the clock frequency, we can make our circuit work faster. But we can't go on increasing the frequency blindly because the delays of the combinational and sequential circuits used imposes some constraints on the maximum frequency that can be used without the output going unpredictable. Also, high frequency means high power requirement of the circuit. So the designer has to decide between speed and power of the circuit. Let's see what are these timing constraints. For that, consider a general circuit with two flip-flops with some combinational circuit in between. Let's draw its timing diagram. Output Q1 of flip-flop 1 starts to settle after TCCQ and settles at TPCQ. D2 starts to change with respect to Q1 after contamination delay and settles after propagation time. Now, for the output to for the output of flip-flop 2 to be stable at next clock edge, D2 must be stable at least setup time before the next clock edge. This imposes a constraint on maximum clock frequency and is commonly known as setup time constraint. For flip-flop 1, the TPCC-Q plus propagation delay of combinational circuit plus setup time of flip-flop 2 must be greater than the time period of clock for a predictable operation of the circuit. This equation is known as setup time constraint or maximum delay constraint. Also, input of flip-flop 2 D2 must be stable for at least whole time after clock edge. So, the sum of contamination delays TCCQ plus contamination delay of combinational circuit must be greater than hold time. This equation is called as hold time constraint or minimum delay constraint. Setup time constraints set the maximum usable frequency of clock, and hold time constraints must not be violated because it can't be adjusted by increasing the clock, but the circuit itself has to be redesigned to meet the constraints. Now an example to see how we do timing analysis. Given this circuit, we have to perform timing analysis and find the maximum frequency at which the circuit can be used, and check if hold time violations occur or not. For finding the maximum frequency, consider the critical path or the longest path. In this circuit, it will be from A to Y dash or from B to Y dash with two gates in between. Apply the setup time constraints to this path. We get delay from clock to output A TPCQ plus propagation delay of gate 1 plus propagation delay of gate 2 plus setup time of flip-flop 2 must be less than time period Tc. Therefore we get 80 plus 2 times 40 plus 50 must be less than or equal to Tc, which is equal to 210 picoseconds. So the maximum clock frequency is 1 upon Tc, which is equal to 10 to power 12 upon 210, which is roughly equal to 4.7 gigahertz. Next, let us look at the circuit if hold time violations occur or not. For this, consider the shortest path, that is from A to X dash or B to X dash or C to Y dash. All the three paths have the shortest path between the flip-flops. Consider any of these paths. Let's say we consider B to X dash. Then clock to output contamination delay of flip-flop plus contamination delay of G1 must be greater than hold time of this flip-flop. So TCCQ plus TCD, which is equal to 30 plus 25 equal to 55 picoseconds, and hold time is 40 picoseconds. So the condition is satisfied and the circuit functions properly for a clock frequency less than found in this timing analysis. Finally, let's have a look at clock skew. Till now we have assumed that clock reaches every flip-flop at the same time, but practically that is not the case. This may be due to noise, lengths of wire connecting the clocks are different, and other causes. Suppose we have two flip-flops that are supplied with same clock, but the clock 2 reaches after some delay corresponding to clock 1. Then this delay can be represented in timing diagram like this, and it's called as T-skew. When doing timing analysis, we always consider the worst case scenario so that the circuit works under all situations. So let's add clock skew effect also in our timing constraints. Consider the same circuit again, this time with clock skew considered. Considering the worst case, clock to output propagation delay of flip-flop 1 plus propagation delay of the combinational circuit plus setup time of the flip-flop 2 plus skew time must be less than the time period of clock. This constitutes a setup time constraint. Now for hold time constraint, in the worst case, clock to output contamination delay of flip-flop 1 plus contamination delay of the gate, or we can say combinational circuit, must be greater than skew time plus hold time. So these are the two final constraints on a digital synchronous sequential circuit with clock skew included in it. This completes this tutorial on timing analysis, and subscribe this channel for more tutorials.